Hi everyone, welcome to our trustable experiments in Engine 121 by Ella, Enuri, Shou, Samarth, and Yunze. So in this project, we've come up with two experiments with two scenarios. Scenario 1, we have the topic of driving. When we consider driving, we got vehicles with different weights, and here it's traveling up a slope. We want to check that the frictional coefficient on inclines is compatible with a variety of weights so that the car only needs to exert a specified force when traveling up a slope. This brings us to our first experiment. We want to explore the consistency of the friction coefficient when tested against the same materials using different weights. In our second scenario, we have construction work. We want to seek out an effective but temporary solution in determining how much force is required in order to hold a building or bridge up. This is highlighted in the picture I've drawn, where the collapsed building is in red. This brings us to our second experiment, which is to find the amount of force needed in order for the system to reach equilibrium. This involves the usage of tensions, trusses, and the system being in equilibrium. Tension from the wire attached to a pulley system in the background, trusses in the laundry rack, and equilibrium in order for the system to not collapse.
The first experiment we did is about friction, and it was set up as displayed on the screen. The objective of this experiment is to calculate the friction coefficient of 4 different objects when they are placed on a wooden board. In the experiment, a force was applied to the rope which is attached to the wooden board using a pulley. This makes the side of the wooden board with the rope attached to rise. Just as the object on top of the board starts to slide down, we stopped applying the force and recorded the protracted reading. Initially, I planned on adding weight to the end of the rope so that I could gradually lift the wooden board, but as the structure I added to the rope was quite small, it was hard to figure out a solution for that. And since the experiment was to figure out friction coefficient, the tension force of the rope didn't matter. The friction coefficient has a noticeable margin error. This could be due to the fact that the pulley wasn't rotating smoothly, or due to the fact that the flow where the experiment was carried on wasn't leveled. In order to get accurate results, each object was experimented on thrice.
This is a diagram of experiment 1. We have one object placed on wooden board and applied a tension force from ropes that provide an angle in order to make object to slide. As the tension force is gradually increasing, the angle is increasing until the object is slide. Therefore, we can calculate the friction coefficient of the object. Based on a theorized formula, I can calculate the friction coefficient of different objects by using average angle and its weight, because tan theta equals to friction coefficient multiplied by normal force. Substitute angle into the formula to see whether the formula is valid or not. Since all objects produce the same value for their friction coefficient, as the calculation on the left-hand side, the formula is valid. In the experiment, we learned the mass of object is proportional to friction. On the other hand, as we increase the angle, the friction increases as well. However, the margin of error is quite large, which means our experiment is not accurate enough. Since we use a different object to slide, and the increase of tension force is hard to control by hand.
In our second experiment, we aim to measure the relationship between a mass on one side of a structure and the tension of a rope attached to a second mass on the other side. This was done by attaching a pulley system to a truss-like structure or my clothing hanger. I had a roller platform that I placed under one side of the hanger and leveled it out with some wood after realizing how the added change in angles would likely make calculations pretty complicated. I then measured the self-weight of the structure and the container separately and passed the rope through a hanging pulley. And this was then tied to a paint tin I used as the second mass. My brother helped me pour and measure different masses of water. This was poured into the red container, and for each of the 5 mass values of the red container, or mass 1, I recorded the value shown. These are some of the issues that we encountered while doing the experiment. First, the wind, I noticed, had an influence on the tension, and I would have to wait until it died down completely, and there were no external forces being placed on the rope. so I had to wait until it died down to take measurements, which was very time consuming. And could have been small amounts of water left in the containers that would change the mass value. I had to replace the rope a few times due to a changing elasticity as the experiment wore on. And I needed to ensure I used a nylon one that wouldn't stretch at all. We were originally going to do a more complicated friction experiment, but we found it really difficult to execute what we wanted to, and it ended up being a lot more complicated than we initially thought. I was initially going to make measurements with 3 different paint can masses, but I found that the weights that were smaller than the self weight of the clothes hanger itself gave really skewed, nonsensical results, so I decided to just use the paint can that was a greater mass than the clothes hanger.
The 2 diagrams drawn here were used to calculate the tension forces acting along the pulley system. The pulley system is attached to the weight of M2 with a set of weighing scales under M2. The diagram on the right was made to draw attention to the vertical reaction forces at points A and B and the horizontal component at point B. It is shown on the experiment table that different percentages of the total mass of M2 were used, seen on the far left of the table. Also, the second value in the tension column seems to be out of place, considering the other values. The calculations that are later seen confirm that the unusual value is valid. For the calculation results that are to come, these steps were followed in order to determine the final answer for the tension force for the different values of the masses of M used. These steps were derived after the calculation of the tension force for the first mass of 1.31 kilograms. To calculate the tension force, solving for the vertical and horizontal components at each of the 2 pivot points was required. This led to having 4 unknowns, and through the method of forming simultaneous equations, the tension force was able to be found. These are the rest of the calculations performed for masses in rows 3 to 5 for M1. Here, the percentage error between the recorded values and the calculated values is shown. The formula stated on the bottom left was derived and used to perform these calculations. If we look at the results, we can conclude that the percentage error decreases as the tension force and the weight of M2 increases. The working behind these calculations is similar to the ones on the previous slide. We see that the larger the tension force, the smaller the percentage error. From this experiment, we were able to visualize some of the concepts of statics. The experiment was set up in such a way that we were able to spot the triangle shapes in the system, which is related to trusses. The truss figure allows mass 1 to be varied safely and provides a platform for it to rest on. Essentially, it shows that a downwards force acts on the platform where the mass is placed. When we take the sum of the forces to equal 0, the tension force calculated is similar to the recorded one. Lastly, the different tension forces in the pulley rope and M2 allow the readings on the weighing scale to vary. Some things we were able to learn from carrying out this experiment was that the tension force does influence the reading of the scales when set up in such a way. The reaction forces at the pivot points are very important to calculate before solving a question related to trusses. Lastly, we know that regardless of an error occurring or not, it is necessary to repeat the experiment multiple times to reduce errors.
That it's good to check against other formula in order to verify our results. Be careful when calculations get too long and careless errors can pop up, and that teamwork makes the dream work. Thanks everyone, and have a nice day.